So in the last lectures we have seen connectedness, path connectedness, and then the concepts of connected components and path connected components. And in this lecture we will talk about a couple of related notions, which are that of local connectedness and local path connectedness. So what does it mean to be a locally connected space? So the idea is that each point has an arbitrarily small connected neighborhood. So for example, if you take the real line and say you take the interval 0, 1 and let's say -1 -half, something like this, then this is not a connected space, but it is locally connected, because every point, if you take any point in any of the intervals, you can take an interval small enough which is connected. So what is meant by arbitrarily small? It means that given any such neighborhood, there exists a further neighborhood which is connected. So given any neighborhood of a point, there exists a further neighborhood which is connected. And so this is the meaning of arbitrarily small connected neighborhood. So how do you define it precisely? Let me give the definition. So here's the definition of local connectedness. So a topological space X is called locally connected at some point X in X if any neighborhood U of X contains a connected neighborhood V that further contains X. So X is contained inside some V which is contained in U, and V is connected. So you have some point X and you have an open neighborhood U of X, and then there is a smaller neighborhood V of X which is connected. So X is called locally connected if it is locally connected at each of its points. So every point has this property. And similarly, you can define locally path connectedness. So X is locally path connected at some point X if any neighborhood U of X contains a path connected neighborhood V. So just replacing connectedness with path connectedness, you get the concept of locally path connectedness. And so X is called locally path connected if it is locally path connected at every point. Now before we see examples of locally connected and locally path connected spaces, let's prove a couple of theorems regarding these two concepts, and then we will move to examples. So the first theorem says that X is locally connected if and only if for every open set U, each of its connected components are open in X. So let us see a proof of this theorem. So suppose first that suppose X is locally connected, then we need to show that for any open set U, each of its connected components are open. So let U be open and let C be a connected component of U. So now if X belongs to C, by the definition of local connectedness, there exists an open neighborhood of X, say V, such that X is contained in V and this is contained inside U. On the other hand, since V is connected, this implies that V must be a subset of the connected component C. And so now we have found for each point X an open set V that is contained inside C. So this means that C is open. open in X. And to show the other way around, so suppose now that all connected components of open sets are open, and to show that X is locally connected, take any point X and an open neighborhood of X and a U, a neighborhood of X. And so now we have to find a V. So to show that there exists a connected neighborhood V of X such that X is in V and it is a subset of U. But V is precisely one of the connected components of U which are open by our hypothesis. So take V to be the connected component containing X, and so this means that X belongs to V and V is a subset of U, so connected component here of U. Okay, so connected component of U that contains X, and so this condition is fulfilled and we see that X is locally connected. And a similar theorem holds for path connectedness rather than simply connectedness. So X is locally path connected if and only if for any open set U, again for any open set U, all its path components are open in X. Open in X. And the proof is very similar to the one I just gave for connected components, and the proof here I am leaving as an exercise for you to do. And just by following the previous arguments you can prove this. Now we have the following theorem which states that first of all that each path component of X lies in a connected component, and the second part is that X is locally path connected, then the connected components and the path connected components are the same. So this gives a condition, useful condition, when the connected components and the path connected components coincide. And so for the proof, for the first part, just observe that path connectedness implies connectedness, path connected implies connected. So every path component is connected, and so lies in a connected component. So this is almost obvious. For the second part, if your space is locally path connected, then you have to show that connected components and path connected components are the same. Here we see that every path component lies in a connected component, but now we have to show that these two are the same. So for this, suppose that X lies in a connected component C, and there is a path connected component which contains X. So let P be the path component containing X. So we have X is in P, and P is a subset of this connected component C, and we have to show that P is actually equal to C, and for this we assume the contrary, so which is that suppose that P is a proper subset of C. Now let Q be the union of path components of X that intersect C. So Q can be written as the union of path components, say P alpha in J, such that P alpha intersecting with C is non-empty. And now this will lead to a contradiction, because we will have a separation for this connected space C. So if X is locally path connected, then what we have is that first of all, C is the union of P and Q, because P is one path component and Q is all the other path components of X that intersect C. So C is the union of P and Q, and this is a disjoint union, and the only thing to show is that P and Q are open. Here of course we should add that P alpha is not the same as P, so this is the union of all other path components apart from P which intersect C. So now we only have to show that these two sets P and Q are open, but this follows that P and Q are open follows from the previous theorem 4.2, which says that if you have an open set, then all its path connected components are open when X is locally path connected. So here you have the set C, which is the disjoint union of P and Q, and in particular if you take in that theorem U to be X itself, then it shows that P and Q are open because it's a path component for the open set X. So P is a path component and Q is a union of path components, each of which are open, so they are both open, and so we have a disjoint union of non-empty open sets, and this is a contradiction that C we say that PQ is a separation. PQ is a separation of C, which is a contradiction since C is connected. C is connected. So now that we have these useful theorems, let's look at some examples. So the first example is that if you take any interval in R or even array, so these are connected, this is connected as well as locally connected, and in fact they are also path connected and locally path connected also. path connected and locally path connected. On the other hand, if you take any Euclidean ball in Rn, then it is also connected and locally connected, and same as above, also path connected and locally path connected. So let me just write path connected PC and locally path connected LPC. Similarly, if you have the set, let's say 0 1 union 2 3, this is not connected but it is locally connected, is not connected, so in fact not path connected, and but locally connected and locally path connected, and locally path connected as well. Another example is the set of rationals which is neither connected nor locally connected. So the proof that it is not connected also works for any open set within an open set, so it is also not locally connected. Now let us look at another more sophisticated example of a space which is locally connected but not. Now for the topologist's sine curve, we see that it is connected. We have already seen it is connected. We have seen it is not path connected. But it is also not locally connected. So to see that it is not locally connected, we can try to see what happens in the vertical segment that we had before. This is 0 cross minus 1 1, which we called V, and then we had the part S, which was just the graph of the function sine 1 over x, something like this. And then if you take a point, let's say here, and take an open neighborhood of this point, then so this is the open neighborhood U, and now U will not have all its connected components open, because so for example this part is a connected component, this part is a connected component, and there will be a connected component that contains this entire segment. So let me call this segment P. So P is contained inside a connected component, but if you take any point, let's call this point X, but X in P does not have an open neighborhood or an open basis set, and a basis set. So this is in the subspace topology for the for this topology sine curve. It does not have a basis set that contains X and contained inside P, contained inside the connected component at P. So this connected component, let me call it C, so contained inside C. So it is not locally connected by our characterization of locally connected spaces, in which every open set had all its connected components open. Similarly, it is not locally path connected either. Just because it is not locally connected, it is not locally path connected. Locally connected, because locally path connectedness implies locally connectedness. So I want you to go through this proof carefully and make this geometric argument rigorous, and convince yourself that it is not locally connected. And once it is not locally connected, we can deduce that it is not locally path connected either.